What if everything we know about the universe's beginnings is just the tip of an unimaginable cosmic iceberg? Picture this: a single point, smaller than an atom, holding the seeds of every galaxy, star, and planet we see today. In the blink of an eye, it erupted into existence, setting the stage for everything that followed. But here's the mind-bending part. Those first fleeting moments after the Big Bang remain one of the greatest unsolved mysteries in science. For decades, the brightest minds have wrestled with the question, what really happened in those first fractions of a second? The answers defy logic. Some theories suggest the universe didn't just explode into being. It might have been born from a collision of higher dimensional realities, or even emerged from a cosmic rebound of a previous universe. Others propose that time itself didn't exist before that moment, meaning the question of what came before might not even make sense. And then there are the wilder ideas, like the possibility that our universe is just one bubble in an infinite cosmic foam, each with its own laws of physics. These aren't science fiction. These are real, cutting-edge hypotheses debated by physicists today. That's exactly what we're diving into: 30 of the most astonishing theories about the universe's first moments. From cosmic inflation to quantum fluctuations, from multiverses to holographic beginnings, each idea is more extraordinary than the last. Some will challenge everything you thought you knew. Others might leave you questioning reality itself. But one thing's certain: by the end of this journey, you'll never look at the night sky the same way again. So let's peel back the layers of time and explore what science and imagination have to say about how it all began. Let's start with the most iconic theory of all, the Big Bang Singularity. Imagine cramming everything in the universe, every galaxy, every star, every speck of dust, into a single point so tiny it has no size at all. That's the mind-boggling idea at the heart of this model. According to the classic Big Bang theory, our universe burst forth from this unimaginably dense and hot state around 13.8 billion years ago. In less than a fraction of a second, it began expanding faster than the speed of light, a process called cosmic inflation, scattering the seeds of matter and energy that would eventually form everything we know. But here's where things get tricky. The term Big Bang might make you picture an explosion in empty space, but that's not quite right. There was no space before it happened, no time, no matter, nothing. The singularity wasn't just a tiny dot floating somewhere. It was the entirety of existence, and that's why physicists call it a singularity, a place where the laws of physics as we know them break down completely. Gravity becomes infinitely strong, temperatures and pressures reach values that defy measurement, and our best equations simply stop making sense. This theory isn't just speculation. It's backed by some of the most compelling evidence in cosmology, like the cosmic microwave background, the faint afterglow of that primordial heat, still detectable today. Or the way distant galaxies are racing away from us, tracing back to that initial expansion. Yet for all its success, the Big Bang model leaves glaring questions unanswered. What triggered that expansion? What existed, if anything, before the singularity? And how did a universe born in chaos settle into the precise conditions needed for stars, planets, and life to exist? These gaps are why scientists keep searching for deeper answers, pushing beyond the singularity into even wilder possibilities. The Big Bang Singularity leaves us with more questions than answers, but what if there was a missing piece to the puzzle? Enter cosmic inflation, a theory so elegant it rewrote our understanding of those first unimaginable moments. Proposed by physicist Alan Guth in the 1980s, inflation suggests the universe didn't just expand. It exploded outward at speeds beyond comprehension, stretching from smaller than a proton to the size of a grapefruit in less than a trillionth of a second. This wasn't just rapid growth. It was exponential, like blowing up a balloon to the size of the observable universe in the time it takes light to cross a single atom. So why does this matter? Inflation solves two cosmic mysteries that left scientists scratching their heads. First, the horizon problem. Look at the night sky in opposite directions, and you'll see galaxies with nearly identical temperatures, yet these regions are so far apart. Light hasn't had time to travel between them since the Big Bang. How could they possibly sync up? Inflation's answer: they were once neighbors. Before that hyper-fast expansion, the entire observable universe was tiny enough to reach thermal equilibrium, like a cup of coffee cooling evenly before being stretched apart. Second, the flatness problem. Our universe's geometry is suspiciously balanced, like a pencil perfectly upright on its tip. Too much matter and space would curve inward. Too little and it would bend outward, yet measurements show space is flat to an astonishing degree of precision. Inflation explains this by stretching the universe so immensely that any initial curvature became imperceptible, just as blowing up a balloon makes its surface appear flatter. But here's the catch. While inflation fits the data beautifully, direct proof remains elusive. We've detected ripples in the cosmic microwave background that align with predictions, like fossilized fingerprints of quantum fluctuations magnified by inflation. Yet competing theories like bouncing cosmologies or variable speed light offer alternative explanations. And then there's the multiverse elephant in the room. If inflation never truly stops, could it spawn infinite bubble universes beyond our own? Guth's theory reshaped cosmology, but the final chapter on those first moments is still being written. What if the Big Bang wasn't a one-time event, but just one heartbeat in an endless cosmic cycle? This is the radical idea behind the cyclic universe theory, a vision of time without beginning or end, where universes are born, die, and are reborn in an infinite loop. At the heart of this model is the concept of the Big Crunch, a mirror image of the Big Bang where gravity eventually overcomes expansion, pulling all matter back into a singularity. From that collapse, a new universe erupts and the cycle begins again. It's a cosmic phoenix rising from its own ashes over and over across eternity. One of the most compelling versions of this idea comes from Nobel laureate Roger Penrose, who proposed something even stranger: conformal cyclic cosmology. Instead of a violent crunch, Penrose suggests that as our universe expands toward heat death, all particles lose mass due to extreme stretching, and space-time itself becomes smooth and empty. At this point, the end of our universe mathematically mirrors the beginning of another, creating a seamless transition. His theory implies that the cosmic microwave background might contain echoes of past universes, ghostly imprints of black holes from eons before our own. The implications are staggering. If Penrose is right, the Big Bang wasn't the absolute beginning, just a reset button pressed by physics we don't yet understand. It challenges the very idea of a singular creation event, replacing it with an endless tapestry of universes, each inheriting subtle traces of the last. Critics argue that cyclic models struggle to explain how entropy, the universe's tendency toward disorder, resets with each cycle. But supporters counter that quantum gravity or undiscovered physics could rewrite the rules at these extreme scales. Either way, the theory forces us to rethink time itself not as a straight line, but as a wheel turning forever in the dark. Now let's step into one of the most dizzying ideas in modern cosmology: the multiverse. What if our universe isn't the only one? What if it's just a single bubble in an endless cosmic foam, each with its own unique rules of reality? This isn't just speculative fiction. It's a serious scientific framework that emerges naturally from two of physics' most profound theories: eternal inflation and string theory. Take eternal inflation first. Imagine the universe isn't just expanding, it's a runaway process, with space stretching exponentially faster than light in some regions while slowing down in others. Where inflation stops, a new universe crystallizes, like a bubble forming in boiling water. But elsewhere, the stretching continues endlessly, creating an infinite tapestry of bubble universes, each with its own Big Bang, its own physics, even its own dimensions. Some might have stars and planets like ours. Others could be so alien that matter as we know it never forms. Then there's string theory's landscape. According to this idea, the fundamental constants of nature, the strength of gravity, the mass of electrons aren't fixed. They're determined by how tiny, vibrating strings of energy fold into higher dimensions. And with an estimated 10 to the power of 500 possible configurations, string theory suggests there could be universes where gravity is 1,000 times stronger, where time flows backward, or where atoms simply can't hold together. Critics argue the multiverse is untestable, more philosophy than science, but supporters point to subtle clues like anomalies in the cosmic microwave background that might be bruises from collisions with other bubbles. And if we ever detect signatures of a universe with different physical laws, it would rewrite our understanding of reality itself. The multiverse hypothesis doesn't just challenge our place in the cosmos, it redefines what everything even means. What if our three-dimensional universe is nothing more than an illusion, a cosmic mirage projected from information encoded on a two-dimensional surface at the edge of reality? This is the mind-bending proposition of the holographic principle, a theory that blurs the line between science and philosophy. It stems from a startling discovery about black holes. When matter falls into one, it doesn't just vanish. It leaves behind an imprint on the event horizon, like a fingerprint burned into the fabric of space-time. The more scientists studied this, the more they realized something extraordinary. All the information inside a black hole could be perfectly encoded on its two-dimensional surface with no loss of detail. This led to an even wilder thought: what if the entire universe operates the same way? Just as a hologram stores a 3D image on a flat sheet, our reality might be a projection from a vast, hidden boundary we can't perceive. Think of it like a movie screen. We're immersed in the action, convinced by the depth and movement, but everything we experience boils down to pixels on a flat surface. The holographic principle suggests space-time itself could be that kind of illusion, an emergent property of quantum information dancing on a distant two-dimensional plane. Where this gets really strange is with quantum gravity. At the smallest scales, space-time appears pixelated, like a digital image zoomed in too far. The holographic principle could explain this granularity by treating space as a network of entangled information, not an absolute backdrop. Some versions of string theory even propose that our universe floats within a higher dimensional space, with all its events written like code on an unimaginably vast cosmic hard drive. Critics argue the theory is untestable for now, but experiments like the holometer at Fermilab are searching for telltale quantum fuzz in space-time that might betray its holographic nature. If they find it, we'd have to confront a staggering truth. Reality isn't just stranger than we imagined, it might be stranger than we can imagine. The holographic principle doesn't just challenge our place in the cosmos, it redefines what place even means. The idea that our entire universe could be nothing more than a random burp in an endless quantum void sounds like science fiction, but it might just be the most elegant explanation yet for how everything began. At the tiniest scales, empty space is anything but empty. Thanks to Heisenberg's uncertainty principle, particles and antiparticles constantly blink in and out of existence, borrowing energy from the void before vanishing again. These quantum fluctuations aren't just mathematical quirks. We've detected them in labs like the Casimir effect, where two metal plates in a vacuum inexplicably attract each other because of these ghostly particles. Now stretch this idea to its COSM, I see Chinese letter. What if the Big Bang was simply a fluctuation on an unimaginable scale, a subatomic bubble of space-time that, instead of popping immediately, somehow stabilized and expanded into the universe we know? In this wild scenario, nothingness isn't truly empty, it's a churning ocean of potential universes, most collapsing instantly, but ours just happened to hit the cosmic lottery. The numbers defy comprehension. The odds of a fluctuation producing our universe have been compared to randomly assembling a fully functional jetliner by throwing scrap metal into a tornado. Yet here's where physics throws us a lifeline. Under certain quantum gravity theories, a newborn universe could borrow energy from the multiverse's zero-energy balance sheet, essentially creating itself from nothing without violating conservation laws. Some models even suggest that once inflation kicked in, the universe's own gravitational energy perfectly cancelled out all other energy, leaving the cosmic books balanced at zero. It's like taking out a loan to build a house, then discovering the house generates exactly enough rent to pay off the debt. The implications are staggering. If this theory holds, our universe might be one of countless quantum hiccups in an eternal void, each with random physical constants. Most would be stillborn or chaotic, but in a few, like ours, the numbers align just right for galaxies, planets, and life to emerge. Critics argue this pushes the limits of testability, but supporters point to deep mysteries like dark energy. Could its inexplicable strength be a fingerprint of our universe's quantum origins? Whether ultimate answer or placeholder for deeper truths, quantum fluctuation theory forces us to confront a humbling possibility. Everything we cherish might exist because once upon a time nothing blinked. The Big Bang paints a picture of a universe bursting forth from nothingness, but what if that explosive beginning was actually a cosmic comeback? Enter the Big Bounce, a theory that rewinds the tape further, suggesting our universe wasn't born from a singularity, but from the death throes of a previous one. Imagine a cosmic accordion. Instead of expanding endlessly or fading into cold emptiness, the universe collapses under its own gravity, reaching a point of unimaginable density, only to rebound in a fiery resurgence. This isn't science fiction. It's a serious contender in the quest to explain those first moments, blending Einstein's relativity with the fuzzy rules of quantum mechanics. Here's how it works. In the traditional Big Bang model, gravity's pull weakens as the universe expands, but the Big Bounce flips the script. Picture a universe so old and vast that expansion finally slows, halted by dark matter and energy. Galaxies reverse course, hurtling toward one another. Space crumples like a sheet of paper, temperatures skyrocket, and everything, every atom, every photon, is crushed into a quantum soup. Then, just as collapse seems inevitable, quantum physics steps in. At scales smaller than an atom, gravity might behave differently, repelling instead of attracting. This quantum pressure could halt the collapse and trigger a rebound, a cosmic reset button that births our universe from the ashes of its predecessor. The beauty of this model, it sidesteps the singularity problem. Unlike the Big Bang's infinitely dense starting point where physics breaks down, the bounce suggests a near singularity, dense enough to warp spacetime but not enough to erase the laws of nature. It's like squeezing a spring, push too hard and it snaps back. Quantum gravity theories like loop quantum cosmology provide the math to support this, showing how spacetime might be granular at tiny scales, preventing true infinite collapse. But the bounce isn't without wrinkles. Critics point to entropy, the universe's tendency toward disorder. If each cycle inherits the previous one's chaos, shouldn't our universe be far more disordered by now? Some bounce models counter this by suggesting entropy resets during the rebound, or that new physics we haven't discovered yet could smooth out the chaos. Others propose that dark energy, still poorly understood, might hold the key to cycling universes cleanly. What's at stake isn't just a tweak to cosmology, it's a radical rethinking of time itself. If the bounce is real, the Big Bang wasn't a beginning but a turning point in an eternal rhythm. Telescopes scanning the cosmic microwave background for concentric rings, ghostly echoes of pre-bounce black holes, could one day tip the scales. Until then, the Big Bounce stands as a tantalizing reminder. Our universe's first chapter might be just one verse in an endless cosmic poem. What if the universe we think we know, with its galaxies, black holes, and laws of physics, is nothing more than lines of code in an unfathomably advanced computer program? This isn't a plot twist from a sci-fi movie. It's the simulation argument, a theory that sparked fierce debate among physicists, philosophers, and even tech billionaires. At its core is a simple but staggering question. If civilizations eventually gain the power to create hyper-realistic simulations of conscious beings, wouldn't the number of simulated minds vastly outnumber real ones? And if so, what are the odds we're among the lucky few living in base reality? The idea gained traction in 2003 when philosopher Nick Bostrom laid out his now famous trilemma. He argued that at least one of these statements must be true. One, almost all civilizations at our level of technological development go extinct before achieving simulation capabilities. Two, advanced civilizations lose interest in creating ancestor simulations, perhaps due to ethical concerns or shifting priorities. Or three, we are almost certainly living inside a simulation. There's no middle ground. If future civilizations survive and choose to run simulations, the sheer number of virtual universes they could generate would make the chance we're in the original reality vanishingly small. Scientists aren't just philosophizing about this, some are actively looking for proof. Physicist Silas Bean suggested simulated universes might have detectable pixelation at extremely small scales, like a video game revealing its resolution limits when zoomed in too far. Others propose searching for mathematical glitches, constants that change in ways real physics wouldn't allow, like a programmer tweaking gravity as an afterthought. Even the perplexing behavior of quantum particles, which exist in multiple states until observed, has been compared to a simulation optimizing processing power by only rendering details when needed. But the theory has its skeptics. Nobel laureate George Smoot points out that simulating every particle in the universe would require more energy than the universe contains. Others argue consciousness might be fundamentally uncomputable. No algorithm could replicate the raw experience of being. And then there's the deeper philosophical quagmire. If we're simulations, are our creators simulations too, nested in an infinite regression of virtual worlds? Whether you find the idea exhilarating or unsettling, it forces us to confront profound questions about reality's nature. If the universe is a simulation, does that make stars less real? Are our emotions just clever programming? Or does it mean reality is far more malleable than we ever dreamed? The simulation argument doesn't just challenge our place in the cosmos, it redefines what place even means. What if black holes aren't cosmic dead ends, but cosmic wardrobes, portals to entirely new universes hidden inside? This is the spine-tingling premise of the black hole universe theory, where our entire reality might be the offspring of a collapsed star in some higher dimensional cosmos. Think of it like a matryoshka doll of existence. Just as our universe contains black holes that might spawn new universes within them, we could ourselves be nestled inside the event horizon of some long-forgotten progenitor. At the heart of this idea is a radical reimagining of black hole singularities. Normally, we picture them as infinitely dense points where physics breaks down, but what if that breakdown isn't an end but a transformation? When matter crosses a black hole's event horizon, general relativity says it gets crushed beyond recognition. But quantum physics hints that information, the blueprint of reality, can't truly be destroyed. The black hole universe theory bridges these two ideas, suggesting that inside every singularity, space-time reboots, creating a new universe with its own Big Bang. Here's where it gets wild. The physics in these baby universes might not mirror their parents. Some theories propose that fundamental constants, like the strength of gravity or the mass of electrons, get subtly randomized during the rebirth. This leads to physicist Lee Smolens's provocative idea of cosmological natural selection. Much like biological evolution favors traits that boost reproduction, Smolens argues universes inside black holes would evolve toward laws that maximize black hole production. In this view, our universe's finely tuned constants perfect for spawning galaxies and stars aren't luck. They're the result of cosmic Darwinism across countless generations of universes. Evidence for this remains elusive, but tantalizing clues exist. The universe's expansion rate, for instance, sits precariously balanced, fast enough to avoid collapsing back into a singularity, but slow enough to let matter clump into black hole factories. And then there's dark energy. Its mysterious strength might be a fingerprint of our universe's black hole ancestry, tweaking expansion just enough to optimize future offspring. Critics counter that without observable links to a parent universe, the theory leans on speculation. But supporters point to black hole entropy calculations that align suspiciously well with conditions needed for universe formation. Whether ultimate truth or stepping stone to deeper understanding, the black hole universe theory does something remarkable. It turns the most destructive objects in existence into cosmic cradles, weaving death and birth into a single, endless story. What if gravity isn't the universe's primary architect, but just a background player in an electromagnetic symphony? This is the bold claim of plasma cosmology, a theory that flips modern astrophysics on its head. While mainstream science paints the cosmos as a gravity-dominated arena, with invisible dark matter gluing galaxies together, plasma universe proponents argue we've been overlooking an obvious force: electricity. Picture the universe not as a static sea of isolated islands, but as a dynamic, crackling web of charged particles, a place where cosmic filaments glow with currents powerful enough to sculpt galaxies. At the heart of this idea is plasma itself, the fourth state of matter, an electrified soup of ions and free electrons that makes up 99% of the visible universe. From lightning to neon signs, we see plasma's behavior in action every day. But plasma cosmologists take it further, suggesting that galaxies and clusters align along vast, twisting circuits of electric current, forming structures that mirror the intricate patterns in a lab's plasma globe. These cosmic power lines, they argue, could explain the filamentary structures we observe, like the billion light-year-wide cosmic web, without invoking mysterious dark matter. The evidence starts with galactic spirals. Gravity alone struggles to explain how galaxies maintain their pinwheel shapes over billions of years without flying apart. Plasma cosmology points to the Birkeland current, a twisting flow of charged particles along magnetic fields, as the invisible hand shaping and stabilizing these structures. Then there's the mysterious void problem. The universe isn't just clumps of matter, it's full of eerily empty regions between galaxy clusters. Plasma models suggest these voids are natural byproducts of electromagnetic repulsion, where opposing currents push matter into dense walls and leave emptiness between them. But the most provocative claim, that the redshift of distant galaxies, the key evidence for cosmic expansion, might not be caused by the Doppler effect at all. Plasma physicist Hans Alfvén proposed an alternative. Double layers of charged particles could shift light's wavelength as it travels through interstellar plasma, mimicking an expanding universe without the need for a Big Bang. Mainstream cosmologists remain skeptical, citing gaps in plasma physics' ability to explain the cosmic microwave background or precise galaxy rotation curves. Yet as anomalies pile up, like unexplained magnetic fields threading the void between galaxies, even critics admit electromagnetism's role in cosmology might be overdue for a second look. Whether paradigm shift or fringe idea, plasma cosmology forces us to confront an electrifying possibility. We might be living in a universe far more charged than we ever imagined. Picture two infinite parallel sheets floating in a higher dimensional space, not just flat and static, but rippling like cosmic flags in an unseen wind. Now imagine them hurtling toward each other until bang, they collide with such force that the energy ignites an entire universe. This isn't abstract poetry. It's the Ekpyrotic scenario, a bold alternative to cosmic inflation that rewrites the origin story of everything using the mind-bending mathematics of string theory. The name comes from the Greek word for conflagration, and it's easy to see why. In this model, our universe isn't the result of a singularity exploding outward, but the aftermath of a cataclysmic clash between higher dimensional objects called branes, short for membranes. Think of them as cosmic sheets, but not the flimsy kind. These could be three-dimensional like our universe, or even higher, existing in a space with dimensions beyond our perception. When they smash together, the energy doesn't just vanish, it condenses into matter, radiation, and the very fabric of space-time, birthing a new cosmos from the wreckage. What makes this theory so compelling is how it tackles inflation's biggest puzzles without invoking exponential expansion. Take the horizon problem. Just like inflation, the Ekpyrotic scenario suggests the early universe was small enough for everything to thermalize before being stretched, but instead of inflating, it was crushed flat. Picture kneading dough until every air bubble disappears. The brane's collision would smooth out irregularities, leaving the uniform cosmos we observe today. And the flatness problem. The brane's near-perfect alignment before impact would naturally produce a universe balanced on the knife edge of geometry we measure. But the Ekpyrotic model goes further, making predictions that could distinguish it from inflation. One key difference lies in gravitational waves. Inflation's rapid expansion would have sent violent ripples through spacetime, potentially leaving a detectable imprint in the cosmic microwave background. The Ekpyrotic scenario, though, predicts far weaker primordial waves, something future telescopes like the Laser Interferometer Space Antenna might confirm or rule out. Another clue could lurk in the distribution of galaxies. While inflation stretches quantum fluctuations into large-scale structures, brane collisions might leave distinct patterns in the universe's scaffolding, like fingerprints on a cosmic window. Critics highlight challenges like explaining how branes avoid shredding apart during collision or why they'd move so perfectly in sync. Yet supporters point to string theory's math, where such brane dynamics emerge naturally. And there's a philosophical allure to the idea. Rather than a universe born from nothing, ours might be one chapter in an endless cycle of brane collisions, each resetting the cosmic clock. Whether ultimate truth or stepping stone, the Ekpyrotic scenario forces us to reckon with a profound possibility. The Big Bang might not have been a beginning but an echo. We think of the Big Bang as the ultimate starting line, the moment when time itself flickered into existence. But what if the clock was already ticking? Some of the most daring theories in physics suggest that time might not have begun 13.8 billion years ago. It could stretch infinitely backward, with our universe just one chapter in an epic without a first page. Take loop quantum cosmology, a framework that treats spacetime like a fabric woven from tiny, indivisible threads. Unlike classical physics, where the Big Bang crunches everything into a meaningless singularity, this model proposes something extraordinary, a cosmic rebound. Picture spacetime not as a one-way street ending in oblivion, but as a trampoline. When the collapsing universe reaches a certain density, quantum effects kick in like an invisible hand, reversing the collapse into an expansion. No singularity, no breakdown of physics, just an endless cycle of contraction and rebirth. In this view, our Big Bang wasn't a true beginning, but a turning point in an eternal dance. This reshapes everything. If time predates our universe, then the question, what happened before the Big Bang, isn't a paradox, it's a valid puzzle with real answers. Some models even suggest traces of the previous universe might linger in ours. Imagine finding fingerprints in the cosmic microwave background, anomalous patterns that can't be explained by our universe's physics alone. Nobel laureate Roger Penrose calls these Hawking points. theorized to be imprints of supermassive black holes from an earlier cosmic cycle, their radiation somehow preserved across the bounce. But loop quantum cosmology isn't the only game in town. String theory offers another twist with its ekpyrotic scenario, where our universe is one sheet in a higher dimensional stack, colliding with another to ignite the Big Bang. Here, time flows continuously in the unseen bulk dimensions, making our cosmic explosion more like a localized event in a far grander timeline. Even general relativity, Einstein's masterpiece, allows for solutions where time extends beyond the Big Bang under certain conditions, like a bridge arching over the singularity. Critics argue these ideas stretch the limits of testability. How do you observe a pre-Big Bang era when all evidence seems obliterated by the explosion? Supporters counter that subtle signatures, like gravitational waves with unexpected frequencies or anomalies in the distribution of galaxies, could betray our universe's cyclical nature. The European Space Agency's Euclid telescope is already hunting for such clues, scanning the sky for patterns that defy standard inflation. The implications are staggering. If time has no true beginning, then the universe isn't something that happened, it's something that's always happening, an infinite kaleidoscope of creation and destruction. This doesn't just change cosmology, it rewrites our deepest myths about existence. After all, humanity has always longed for origins, the first spark, the primal cause. But the universe, it seems, might prefer an endless encore. Dark energy was supposed to be the universe's quiet crescendo, a gentle force pushing galaxies apart until the cosmos faded into cold, endless night. But what if we've got it all wrong? Imagine a universe where dark energy isn't just persistent, it's growing stronger over time, accelerating expansion until space-time itself is torn apart atom by atom. This nightmare scenario is called phantom energy, and it doesn't just rewrite the universe's future, it could reshape our understanding of its birth. The math behind this is as beautiful as it is terrifying. In standard cosmology, dark energy has a constant strength, represented by the cosmological constant in Einstein's equations. But phantom energy flips the script. Its density increases as the universe expands, like a car that accelerates faster the longer you press the gas. If that sounds impossible, consider this. We've already observed dark energy's repulsive force driving cosmic expansion. The phantom scenario simply takes this to its logical extreme, suggesting dark energy's equation of state, the ratio of its pressure to density, could dip below -1, crossing a threshold that defies conventional physics. Here's where it gets apocalyptic. If phantom energy exists, the universe's fate isn't just expansion, it's disintegration. First, galaxy clusters will be ripped apart as accelerating expansion overcomes gravity's grip. Then individual galaxies would unravel, stars flung into the void. In the final moments, even atomic bonds would fail, protons torn from neutrons in a last scream of spacetime. Cosmologists call this the Big Rip, an end so violent it makes black holes look tranquil. But phantom energy's implications reach far beyond doomsday predictions. If dark energy's strength can evolve, it might hold clues about the Big Bang itself. Some models suggest phantom behavior could have been inverted in the early universe, acting as an attractive force rather than a repulsive one. Picture a cosmic seesaw. As phantom energy's push dominates today, its pull might have dominated back then, sculpting the initial conditions of reality. This could explain why the universe started with such unnervingly precise balance, its expansion rate fine-tuned to avoid immediate collapse or chaotic dispersal. Not everyone's convinced. Critics point to measurements of dark energy's equation of state, which currently align neatly with Einstein's cosmological constant. But supporters highlight tantalizing anomalies, like the Hubble tension, where different methods of measuring cosmic expansion yield slightly conflicting results. Could this discrepancy hint at dark energy's phantom nature lurking just beyond our current instruments' reach? future telescopes like the Vera-Rubin Observatory aim to settle the debate by mapping billions of galaxies, hunting for phantom energy's fingerprints in the stretching fabric of spacetime. Whether ultimate truth or mathematical phantom, this theory forces us to confront a humbling reality. The force we thought was quietly guiding the cosmos might be anything but gentle. And if the universe can end in a rip, not a whimper, what other explosive secrets might dark energy be hiding about how it all began? What if the universe didn't have a dramatic beginning at all? No big bang, no singularity, just a quiet transition from stillness to motion, like a sleeping giant slowly stirring awake. This is the essence of the emergent universe theory, a radical reimagining of cosmic origins that swaps fireworks for a gentle unfolding. At its core is a simple but profound shift in perspective. Instead of asking, how did the universe begin? We might need to ask, how did change emerge from timelessness? Think of a frozen lake at winter's end. There's no precise moment when ice becomes water, just a gradual shift as temperatures rise. The emergent universe model applies this logic to reality itself, proposing that our cosmos didn't explode into being but transitioned from a timeless, unchanging state called the Einstein static universe. In this primordial phase, space existed but didn't expand or contract. Matter and energy were perfectly balanced, like a pencil standing on its tip, until quantum fluctuations, those tiny jitters inherent to reality, nudged the system into motion. Suddenly, balance tipped, and the static universe began to evolve, giving rise to the expanding cosmos we know today. This idea elegantly sidesteps the singularity problem that haunts traditional Big Bang models. No infinite densities, no breakdown of physics, just a smooth passage from one state to another. It also offers a fresh take on the universe's perplexing fine-tuning. Why are the fundamental constants so precisely calibrated for complexity? In an emergent scenario, those values might have been locked in during the static phase, like settings on a control panel before a machine powers up. Where the theory gets truly fascinating is its ties to quantum gravity. Some versions suggest that in the static phase, spacetime was fundamentally quantum a foamy, fluctuating network where concepts like before and after had no meaning. Only when this quantum soup reached a critical threshold did classical spacetime crystallize, bringing time as we know it into existence. This mirrors how ice forms when water molecules align just right, hinting that time itself might be an emergent property, not a fundamental feature of reality. Critics argue the model struggles to explain why the static phase would destabilize in the first place, or how quantum fluctuations could grow strong enough to trigger cosmic expansion. But supporters point to modern quantum gravity research, where timeless states appear naturally in equations like loops in loop quantum cosmology or branes in string theory. And there's potential observational evidence too. If the universe emerged smoothly, subtle imprints might linger in the cosmic microwave background's polarization patterns, distinct from the violent swirls predicted by inflation. The emergent universe theory doesn't just challenge our origin story, it reshapes how we think about existence. If time isn't foundational but emergent, then the very framework of beginnings might be a human construct, not cosmic law. It's a humbling reminder that reality, much like a waking giant, might operate on scales far beyond our intuitive grasp. The universe in its first moments was a seething cauldron of particles so dense and energetic that even quarks, the building blocks of protons and neutrons, couldn't hold themselves together. But what if that primordial soup contained ingredients we've never seen? Enter supersymmetry, one of the most elegant ideas in modern physics, promising to reveal hidden players in the cosmic drama of creation. At its heart lies a tantalizing symmetry, a cosmic mirror that reflects every known particle as a heavier, unseen twin. If proven true, it wouldn't just tweak our understanding of the early universe, it would rewrite the entire recipe. Here's how it works. The standard model of particle physics explains the universe with 17 fundamental particles, from electrons to Higgs bosons. But it's incomplete. It can't explain dark matter, gravity's weakness, or why the Higgs particle is so oddly lightweight. Supersymmetry, or SUSY for short, solves these puzzles by proposing a grand symmetry between matter particles, fermions, and force carriers, bosons. For every quark, there's a hypothetical squark. Every photon gets a shadowy photino. These superpartners would have shaped the early universe in profound ways. Picture the first trillionth of a second after the Big Bang. At these insane energies, superparticles wouldn't just exist, they'd dominate. The universe's expansion would have been fueled not just by quarks and gluons, but by their supersymmetric counterparts slamming into each other at nearly light speed. This changes everything about how we model cosmic inflation. Some SUSY models suggest that the lightest superpartner, often the neutralino, could be dark matter itself, freezing out as the universe cooled like bubbles in hardening amber. But the implications run deeper. Supersymmetry elegantly solves the hierarchy problem, a head-scratcher about why gravity is so laughably weak compared to other forces. With superparticles in play, quantum corrections from the Higgs field would cancel out with mathematical precision, like two waves erasing each other. Without SUSY, the Higgs mass should skyrocket to absurd levels due to quantum effects unless nature fine-tuned the universe with impossible precision. Supersymmetry offers a way out, whispering that we've simply been missing half the cosmic ledger. Yet for all its beauty, SUSY remains elusive. The Large Hadron Collider has hunted superparticles for over a decade with no smoking gun, pushing potential discovery energies ever higher. Some theorists argue SUSY might be broken at scales we can't yet probe, hiding its fingerprints just beyond reach. Others suggest alternative formulations like split supersymmetry, where only certain superpartners exist at accessible energies. The stakes couldn't be higher. If SUSY is real, it would mean the early universe was twice as rich as we thought, a symphony of particles and superparticles dancing in perfect symmetry before breaking apart as temperatures fell. If not, physicists might need to tear up decades of theoretical work and start anew. Whether final answer or stepping stone, supersymmetry forces us to confront a humbling truth. The universe's first moments might have been even stranger and more beautiful than we dared imagine. The early universe presents a paradox that keeps physicists awake at night. It was born suspiciously orderly. According to the fundamental laws of thermodynamics, entropy, a measure of disorder, always increases over time. That's why ice melts in warm water, never the reverse, and why your coffee eventually cools to room temperature. But rewind to the Big Bang and we find something baffling. The newborn universe had staggeringly low entropy, packed into an ultra-fine-tuned state that made all future complexity possible. This isn't just a quirk, it's the ultimate free lunch mystery, and it might hold the key to understanding reality's true origins. Picture a deck of cards fresh from the factory, arranged perfectly by suit and number. That's low entropy. Shuffle it once and it becomes slightly more disordered. Keep shuffling and eventually you'll get random chaos, the natural high entropy state. Now imagine opening a brand new deck only to find it already thoroughly mixed. That's the equivalent of what we'd expect at the Big Bang if thermodynamics behaved normally. Instead, we got the pristine deck, a starting point so finely ordered it enabled galaxies, stars, and life to eventually form. This leads to an explosive question: why did the universe begin in such an unlikely state? One radical answer comes from the late physicist Roger Penrose, who argued that the low entropy beginning wasn't accidental, it was sculpted by a deeper principle we don't yet grasp. His whale curvature hypothesis suggests that at the Big Bang, spacetime's curvature, how it bends and warps, was perfectly smooth. No black holes, no cosmic knots, just an eerily uniform canvas. As the universe aged, gravity introduced wrinkles, increasing entropy by clumping matter into stars and galaxies. But that just pushes the mystery back a step. What forced space-time to start so smooth? Some theorists turn to the multiverse for answers. In an infinite sea of universes, most would begin with high-entropy cosmic junkyards where particles are forever scattered in disarray. Ours, by sheer statistical fluke, might be the rare exception, a lottery winner in the thermodynamic casino. Others propose time might have flowed backward before the Big Bang, with entropy decreasing toward the singularity before flipping direction, like a movie played in reverse until the pivotal moment. But the most mind-bending possibility, that our universe's low entropy birth isn't a starting point at all, but a transitional phase in a cyclical cosmos. If black holes eventually evaporate via Hawking radiation, as quantum physics predicts, they could purge disordered information from the universe, effectively resetting entropy over unimaginable timescales. The Big Bang might then mark not creation, but a cosmic rejuvenation, a universe taking its first ordered breath after an eternity of decay. The thermodynamic beginning forces us to confront an unsettling truth. The universe's apparent birth might be hiding a deeper layer of physics, one where order and time play by rules we're only beginning to glimpse. Whether through multiverses, cyclical time, or undiscovered laws, this mystery reminds us that even something as mundane as the cooling of your coffee might be tracing back to the most profound enigma of all, how existence chose its first moment. Among the many theories vying to replace cosmic inflation, string gas cosmology offers one of the most radical reinventions of the universe's first moments, where the building blocks of reality weren't particles or energy, but tiny, vibrating loops of string. Picture the cosmos not as a rapidly expanding singularity, but as a seething ocean of strings tangled in extra dimensions, their collisions and harmonies eventually sparking everything we know. This isn't just a tweak to the Big Bang, it's a rewrite of creation's first draft with consequences that ripple across modern physics. At its core, string gas cosmology flips the script on inflation's exponential expansion. Instead of a brief, hyper-speed growth spurt, this model proposes that the early universe began as a compact, nine-dimensional space filled with a hot gas of strings. The same fundamental thread string theory suggests make up all particles. These strings didn't just float passively, they wound around the universe's compact dimensions like rubber bands wrapped around a soda can, vibrating at different frequencies to produce the diversity of matter and forces we see today. Over time, as the strings interacted and exchanged energy, three of those dimensions, our familiar space, expanded, while the others remained tightly coiled, hidden from view. What makes this idea so compelling is how naturally it accounts for the universe's large-scale structure. In traditional inflation, quantum fluctuations during rapid expansion get stretched into the seeds of galaxies. But string gas cosmology offers an alternative. The string's vibrations themselves generated those primordial wrinkles. Like plucking a guitar string creates overtones, the string's resonant interactions in the early chaos would have imprinted slight density variations that later grew into galaxy clusters and cosmic voids. Remarkably, this process predicts patterns in the cosmic microwave background that, in some cases, align better with observations than inflation's predictions, particularly at the very largest scales. But the theory's boldest claim lies in its explanation for the universe's eerily perfect flatness and uniformity. Unlike inflation, which forces a brief period of hyper-expansion to smooth everything out, string gas cosmology suggests equilibrium thermodynamics did the heavy lifting. The early string gas was so densely packed and hot that it reached thermal equilibrium long before expansion began, like a cup of coffee stirred until perfectly uniform. This equilibrium state, combined with the string's winding mode stabilizing the compact dimensions, could explain why our universe appears so finely tuned without invoking an ad hoc inflationary field. Critics highlight gaps like the lack of a definitive mechanism for how exactly three dimensions chose to expand while the others stayed small. And without direct experimental evidence for strings themselves, let alone their primordial gas, the theory remains speculative. Yet supporters point to subtle signatures that future telescopes might detect, like unique gravitational wave patterns or anomalies in the distribution of distant quasars. If found, these could hint at a universe not born from a singular explosion, but from the symphony of vibrating strings tuning reality into existence. Whether ultimate truth or stepping stone, string gas cosmology forces us to reconsider the most basic assumptions about beginnings. It suggests that the universe's blueprint wasn't written in the language of particles or fields, but in the harmonies of tiny, dancing threads, their vibrations still echoing in the vast silence of space. Stephen Hawking once joked that asking what happened before the Big Bang is like wondering what lies north of the North Pole. But his no-boundary proposal with physicist James Hartle wasn't just a clever dismissal. It was a complete reimagining of cosmic origins, where the universe simply has no beginning in the traditional sense. Think of time not as a straight line with a starting gun, but as a circle where past and future seamlessly connect, making the Big Bang more like the smooth curve of the Earth's horizon than a definitive edge. At the heart of this idea is a marriage between quantum mechanics and general relativity, two frameworks that famously clash. Hawking and Hartle's breakthrough was treating time as an imaginary dimension at the universe's birth, blending it with space into a four-dimensional continuum where distinctions dissolve. Picture spacetime as a globe. Just as Earth has no edge at its poles, the universe might have no boundary at its origin. In this model, the Big Bang wasn't a violent explosion from nothing. It was a quantum transition, a gentle rounding off of reality where probabilities replaced singularities. This solves one of cosmology's thorniest problems, the singularity. In classical physics, the Big Bang marks a point where equations implode and predictability vanishes. But the no-boundary proposal replaces that chaos with quantum fuzziness. Imagine zooming in on a snowflake. It looks smooth from afar, but up close, its intricate fractal edges emerge. Similarly, at the universe's smallest scales, time and space become probabilistic, blurring the idea of a definitive start. Hawking likened it to the South Pole. You can't go farther south, but the laws of physics don't break down there, they just behave differently. The implications ripple outward. Without a boundary, the universe doesn't need external triggers or pre-existing conditions. Its initial state emerges naturally from quantum mechanics, like a bubble forming in boiling water. This aligns with the observed uniformity of the cosmos, no fine-tuning required, but it also raises profound questions. If time loops back on itself, does causality still hold? Could quantum effects from the future have influenced the universe's birth? Critics argue the proposal is more elegant math than testable science. Yet supporters point to subtle signatures, like specific patterns in the cosmic microwave background's polarization, that could hint at a boundary less past. Other clues might lurk in primordial gravitational waves, their frequencies encoding the universe's first quantum jitters. Ultimately, the no-boundary proposal doesn't just challenge our origin story, it redefines what origin means. If Hawking and Hartle were right, the Big Bang wasn't a beginning at all, but a moment where time itself crystallized from something deeper, a cosmic mirage hiding a truth we're only beginning to grasp. We think of dark matter as the universe's silent scaffolding, an invisible force holding galaxies together. But what if it wasn't just a passive player in cosmic history? What if dark matter was the architect of reality itself, sculpting the universe's first structures before ordinary matter even had a chance to shine? This isn't just wild speculation. Some of the most compelling theories about the early universe suggest dark matter didn't just witness the Big Bang, it might have dictated its aftermath. Take primordial black holes, one of the leading candidates for dark matter's identity. These aren't the black holes we know today, born from collapsing stars. They are hypothetical monsters forged in the furnace of the early universe, when extreme densities could have squeezed matter into tiny, ultra-dense knots. Picture the cosmos in its first second, a seething plasma so hot and thick that random fluctuations might have birthed black holes by the trillions, some as small as an atom, others as massive as a star. If these ancient relics still drift through space today, they could explain dark matter's gravitational grip without invoking new particles at all. But there's another, even stranger possibility. Dark matter might be made of exotic particles that don't just lurk in the shadows, they actively shape the universe's blueprints. Weakly interacting massive particles, or WIMP, are a prime suspect. These hypothetical heavyweights would have emerged in the first fractions of a second after the Big Bang, crashing into each other with enough energy to spark annihilation. As the universe expanded and cooled, they'd freeze out like ice crystals forming in supercooled water, leaving behind a vast, invisible web, the kicker. These particles wouldn't just clump under gravity. Their interactions could have created subtle density ripples that ordinary matter later traced, like ink spreading along invisible grooves. The evidence for dark matter's starring role is etched into the cosmos. Look at the cosmic microwave background, the afterglow of the Big Bang. Its faint temperature variations reveal regions where matter was slightly denser, seeds for future galaxies. But here's the puzzle. Those fluctuations are too smooth to explain the universe's large-scale structure unless something else was pulling the strings. Enter dark matter, whose gravity would have amplified those tiny wrinkles, gathering ordinary matter into the cosmic web we see today. Without it, galaxies might never have formed at all. Yet the mystery deepens when we consider dark matter's quirks. Some models suggest it could have formed dark atoms, bound by unseen forces, or even birthed entire dark stars in the early universe, collapsing not from hydrogen but from dark matter annihilation. Others propose it interacts weakly with itself, creating friction that sculpted the first proto-galaxies into disks instead of blobs. The more we study dark matter's potential fingerprints, the clearer it becomes. This isn't just missing mass. It's the hidden hand that carved the universe into shape. The hunt for answers is far from over. Telescopes like the James Webb Space Telescope are peering back to the universe's infancy, searching for unexpected patterns in the earliest galaxies that might betray dark matter's influence. Particle colliders are smashing atoms together, hoping to conjure WIMP from the void. And if primordial black holes really do lurk in the darkness, gravitational wave detectors might one day catch their collisions ringing through space-time like echoes from creation's dawn. Whatever dark matter turns out to be, its story is inseparable from the universe's birth. It's not just a shadowy bystander, it's the ghost in the cosmic machine, the unseen sculptor whose fingerprints are everywhere we look. And when we finally unmask it, we might not just solve a modern astronomical puzzle. We could rewrite the very first chapter of existence. Imagine the universe's first moments were not just a searing fireball, but a cosmic dynamo, crackling with magnetic energy strong enough to twist spacetime itself. Most of us think of magnetism as something that holds fridge notes or guides compass needles. But in cosmology's wild early days, magnetic fields might have been the invisible architects of everything we see. These fields wouldn't have been the faint whispers we measure today. They'd be monstrous, spanning light years and weaving through the newborn cosmos like threads in a tapestry. The kicker, their fingerprints could still linger in the structure of galaxies, hidden in plain sight. The mystery begins with a puzzle. How did galaxies get their intricate shapes so quickly? Gravity alone moves too slowly to explain the vast, elegant spirals we observe. Enter primordial magnetism. If the universe was born with even a faint magnetic seed, perhaps generated by quantum fluctuations during inflation or violent plasma motions in the first seconds, those fields would have amplified as space expanded. Picture stretching a rubber band covered in iron filings. The farther you pull, the more the particles align, transforming chaos into order. By the time matter clumped into protogalaxies, these magnetic lines could have acted like cosmic scaffolding, channeling gas into dense filaments that collapsed into stars and galaxies far faster than gravity could manage alone. But where would such fields come from? One radical idea ties them to the birth of spacetime itself. During cosmic inflation, when the universe expanded exponentially in a fraction of a second, quantum vibrations in the fabric of reality might have generated electromagnetic waves strong enough to persist through the Big Bang's fireball. Alternatively, phase transitions in the early universe, like water freezing into ice, could have unleashed turbulent plasmas that twisted and knotted magnetic fields into existence. Some theories even suggest these fields were relics of a previous universe, carried over through a big bounce or higher dimensional bridge. The evidence is tantalizing but indirect. Astronomers have detected magnetic fields threading through galaxy clusters, and the voids between them structures so vast they'd need billions of years to form under known physics. Yet there they are, as if etched into the cosmos from the beginning. More clues come from the cosmic microwave background. While no definitive primordial magnetic signal has been found, subtle anomalies in its polarization patterns could hint at hidden forces tugging at the infant universe. Critics argue that magnetic fields would have dissipated too quickly to leave lasting imprints, but supporters counter with simulations showing how these fields could self-sustain, like a dynamo in Earth's core, churning plasma into ordered spirals for eons. If they're right, magnetism isn't just a side effect of cosmic history, it's one of its chief engineers, a force so fundamental it might rewrite how we understand the universe's first blueprints. The implications stretch beyond galaxies. Primordial magnetism could explain cosmic inflation's fine-tuned expansion rate, or even dark matter's distribution. It's a reminder that the universe's grandest structures might owe their existence to forces we're only beginning to measure. Hidden threads woven into reality's fabric when everything was just a whisper of energy in the dark. We take for granted that the universe began as a smooth, uniform soup, a cosmic pint that poured perfectly into the glass of space. But what if that assumption is dead wrong? The anisotropic universe theory dares to suggest that the Big Bang was anything but symmetrical, that the infant cosmos was a lopsided, chaotic place where temperatures, densities, and even the laws of physics varied wildly from one direction to another. Imagine tossing a handful of confetti into the wind, only to watch it scatter in jagged, uneven patterns instead of drifting gently apart. That might be closer to how reality actually began. This idea isn't just philosophical rebellion, it's born from stubborn cosmic anomalies. Look at the large-scale structure of the universe today. Galaxies aren't scattered randomly. They form vast filaments and walls with eerie voids between them, like foam bubbles frozen mid-pop. Then there's the axis of evil, a controversial pattern in the cosmic microwave background where temperature fluctuations appear oddly aligned across the sky, as if the universe has a hidden north and south pole. Mainstream cosmology chalks these up to statistical flukes, but anisotropic models propose their fossils echoes of a time when the universe stretched, heated, and expanded at different rates depending on which way you look. At the heart of these theories lies a radical tweak to Einstein's equations. General relativity traditionally assumes isotropy, that the universe looks the same in all directions. But anisotropic solutions allow for wild variations, where space might have stretched faster along one axis than another, like taffy pulled unevenly. Some versions even suggest that dark energy, the mysterious force accelerating cosmic expansion, could be a relic of this primordial lopsidedness, its strength varying across space like patches on a quilt. The implications are staggering. If true, anisotropy could rewrite the story of cosmic inflation. Instead of a perfectly smooth exponential expansion, the early universe might have undergone directional inflation, where space ballooned rapidly in some dimensions while others lagged behind. This could explain why we observe mysterious large-scale flows, whole galaxy clusters drifting en masse toward unseen gravitational giants. Critics dismiss these as measurement errors, but anisotropic models argue they're cosmic currents left over from creation's turbulent first moments. Here's where it gets truly mind-bending. Anisotropy might not have been random, it could have been sculpted by forces we don't yet understand. Some theories propose that the universe inherited its lopsidedness from a higher dimensional collision, like a brain smash in string theory that left permanent wrinkles. Others suggest that quantum fluctuations in gravity itself, magnified during inflation, imprinted asymmetric patterns that persist today. There's even a wild possibility that what we call the laws of physics might vary subtly across space, with constants like the speed of light or the strength of nuclear forces slightly different in one galactic supercluster versus another. The search for proof is already underway. Next-generation telescopes like the Simons Observatory are scanning the cosmic microwave background for telltale distortions, statistical fingerprints that could betray the universe's uneven infancy. Meanwhile, studies of distant quasars are hunting for variations in fundamental constants across billions of light-years, which would shatter the myth of cosmic uniformity. Whether ultimate truth or provocative thought experiment, anisotropic cosmology forces us to confront an unsettling possibility. The universe might not play fair. Its symmetries could be illusions, its constants anything but constant, its history written not in straight lines but in spirals and knots. And if that's true, then every assumption we've made about reality's beginnings might need a second look, starting with the idea that the cosmos ever began evenly at all. Among the dizzying array of hypothetical particles in supersymmetry, one stands out as both a cosmic architect and a potential time bomb: the gravitino. This elusive particle isn't just another entry in the quantum menagerie, it's the supersymmetric twin of the graviton, the hypothetical carrier of gravity itself. But here's where the story gets wild. If gravitinos exist, their fleeting lives and dramatic decays might have orchestrated the universe's earliest energy distribution, tipping the scales between annihilation and existence as we know it. Picture the universe in its first trillionth of a second, a seething, particle-packed frenzy where energy densities were so extreme that matter and antimatter were constantly colliding and obliterating each other. In this chaos, gravitinos would have been born in abundance, their sheer mass thousands of times heavier than protons, making them cosmic heavyweights. But unlike stable particles that persist, gravitinos are theorized to be unstable, decaying into lighter particles with a cascade of consequences. Some models suggest these decays could have flooded the early cosmos with extra photons and neutrinos, reheating the universe in ways that altered the delicate balance between radiation and matter. But the gravitino's true cosmic power lies in its timing. If these particles hung around too long before decaying, their energy injections might have disrupted nucleosynthesis, the process that forged the first hydrogen and helium nuclei. Imagine a chef carefully timing ingredients for a souffle, only for someone to slam the oven door at the wrong moment. Gravitational waves from these decays could also have left faint imprints on spacetime itself, like ripples from stones tossed into a pond long before life existed to witness them. The stakes are even higher when you consider dark matter. Some versions of the gravitino hypothesis propose it could be dark matter, its decays producing the invisible mass that now binds galaxies together. Others warn that early gravitino decays might have diluted dark matter's density, forcing physicists to rethink its very nature. It's a cosmic tightrope walk. Gravitinos could either solve lingering mysteries or introduce new problems we haven't even anticipated. Experiments at CERN Large Hadron Collider are hunting for gravitino-related signatures, while astrophysicists scour the cosmic microwave background for anomalies that might betray their ancient influence. Whether these particles prove to be missing puzzle pieces or red herrings, their story underscores a humbling truth. The universe's first moments were shaped by actors we're only beginning to imagine, their echoes still whispering across billions of light years. What if dark matter and dark energy, the two greatest cosmic mysteries, weren't separate entities at all, but different faces of the same exotic substance? That's the bold claim of the Chaplygin gas model, a theory that dares to rewrite the universe's energy budget with a single, bizarre fluid. Picture this: an invisible medium that behaves like cold, clumpy dark matter in the early cosmos, exerting gravitational pull to sculpt galaxies, then morphs into a smooth, repulsive force mimicking dark energy as the universe expands. It's not just a convenient shortcut, it's a radical rethinking of how cosmic evolution might really work. The idea hinges on the Chaplygin gas's strange properties. Named after Russian physicist Sergei Chaplygin, this hypothetical substance is neither solid, liquid, nor plasma. It's a perfect barotropic fluid, meaning its pressure depends solely on its density. Early in cosmic history, when galaxies were forming, the gas would have been dense enough to act like cold, dark matter, clustering under gravity to provide the scaffolding for stars and galaxies. But as expansion diluted its density, its pressure would kick in, generating a repulsive effect eerily similar to dark energy's cosmic push. One material, two roles, like an actor playing both hero and villain in the same film. Where this model gets truly fascinating is its implications for inflation. Traditional dark energy models treat it as a late-game addition, a cosmological constant that only dominates after the universe grows old and sparse. But Chaplygin gas suggests a seamless transition, where the same substance that helped birth galaxies now accelerates their separation. Some versions even propose that quantum corrections to the gas's equation of state could have tweaked inflation's early moments, subtly altering how quantum fluctuations stretched into galaxy-seeding wrinkles. Evidence remains elusive, but tantalizing hints exist. The cosmic microwave background's power spectrum, a snapshot of the early universe's density variations, shows anomalies that pure dark matter models struggle to explain. Chaplygin gas, with its evolving behavior, could account for these quirks by smoothing certain fluctuations differently as the universe aged. Even more provocative are observations of large-scale structure. The distribution of galaxy clusters aligns slightly better with Chaplygin-inspired simulations than with standard models in certain scenarios. Yet critics highlight glaring challenges. If Chaplygin gas unified dark energy and dark matter so neatly, why don't we see its fingerprints more clearly in galaxy rotation curves or cosmic voids? Others argue that fine-tuning the gas's parameters to match all observations feels like retrofitting a puzzle piece rather than discovering it. Still, as astronomers uncover more discrepancies in the standard model, like the Hubble tension or oddly clustered quasars, the Chaplygin hypothesis lingers as a reminder that the universe's darkest secrets might hide in plain sight, waiting for us to rethink the rules. Whether ultimate solution or stepping stone, the Chaplygin gas model does something remarkable. It turns the cosmos's greatest mysteries into two sides of the same cosmic coin. And if future telescopes catch a whiff of this exotic fluid's presence, it wouldn't just solve two puzzles at once, it would redefine how we think about the universe's past, present, and ultimate fate. Einstein pictured spacetime as a smooth, unbroken fabric, a stage where the cosmic drama unfolds without gaps or seams. But what if that stage is an illusion? Causal set theory dares to suggest that reality, at its deepest level, isn't continuous at all. Instead, it's made of discrete, indivisible atoms of spacetime, tiny grains of existence that link together like beads on a cosmic necklace, forging the illusion of continuity through their relationships rather than any fundamental fabric. This isn't just a tweak to physics, it's a revolution in how we conceive the universe's birth, where the Big Bang emerges not from a singularity, but from the simplest possible arrangement of these elemental building blocks. Think of it like pixels on a screen. From a distance, images appear smooth, but zoom in close enough, and you'll find individual dots defining the picture. Causal set theory applies this logic to spacetime itself, proposing that what we perceive as a flowing, four-dimensional continuum is actually a vast network of discrete events, each connected by cause and effect. Here's the radical part. Time isn't a river, but a sequence of steps like frames in a film strip. The space between these steps isn't empty, it simply doesn't exist. The universe isn't in space-time, it is space-time built from the ground up by these causal relationships. This elegantly sidesteps one of cosmology's thorniest problems, the singularity. In Einstein's equations, the Big Bang marks a point where curvature becomes infinite and physics breaks down. But in causal set theory, there's no infinitely dense point, just a sparse, ordered structure growing denser as we look backward. The earliest universe might have been a mere handful of spacetime atoms, their connections so minimal that concepts like before and after blur into quantum uncertainty. As more atoms linked, each new connection birthing a moment of time, the scaffolding of reality emerged, eventually giving rise to the universe we recognize. Where this gets mind-bending is its implications for quantum gravity. If spacetime is granular, then the paradoxes haunting black holes and the Big Bang might dissolve. Picture a black hole's event horizon not as a smooth boundary, but as a cascade of causal links breaking apart like a zipper undone. Or consider inflation. Instead of a mysterious field stretching smooth spacetime, the early universe could have undergone a growth spurt of new spacetime atoms crystallizing from quantum foam, their arrangement naturally explaining why the cosmos appears so uniform on large scales. Critics argue the theory is hard to test. How do you detect spacetime grains smaller than a Planck length? Yet supporters point to subtle signatures like faint variations in the speed of light at ultra-high energies or anomalies in cosmic ray showers that could betray spacetime's pixelated nature. Others hunt for mathematical patterns in the cosmic microwave background, hidden correlations that a causal set would imprint like a watermark on creation's first light. The real beauty of causal set theory lies in its simplicity. No extra dimensions, no unseen brains, just the bare-bones structure of cause and effect, weaving reality from the ground up. Whether ultimate truth or stepping stone, it forces us to confront a profound shift. The universe might not have a stage. It might be the play itself, performed on a scaffold of moments we're only beginning to count. The holographic Big Bang theory takes one of the most mind-bending ideas in physics, that our three-dimensional reality might be a projection from a two-dimensional surface, and applies it to the very birth of the cosmos. Imagine the universe's first moments not as an explosion in space, but as information flickering to life on some unimaginable cosmic hard drive. Every quark and photon encoded in bits more fundamental than the atoms they'd eventually form. This isn't just a poetic metaphor, it's a radical reimagining of creation that could solve some of the Big Bang's deepest paradoxes. The story starts with black holes. When matter falls into one, it doesn't vanish, it leaves an imprint on the event horizon, like a shadow burned into the fabric of space-time. The more physicists studied this, the clearer it became. All the information inside a black hole could be perfectly stored on its two-dimensional surface without losing a single detail. This revelation birthed the holographic principle, the idea that our three-dimensional universe might similarly be written on a distant two-dimensional boundary we can't perceive. Apply that to cosmology and suddenly, the Big Bang's infinite densities and singularities start to look less like physical impossibilities and more like computational glitches in how we've been reading reality's code. In this model, the early universe wasn't a seething ball of energy in space, it was data. The holographic Big Bang suggests that what we perceive as the violent expansion of matter and radiation was actually the decoding of information from some primordial lower-dimensional surface. Picture a movie projector. The vivid three-dimensional world on screen emerges from patterns of light on a flat film. Similarly, the cosmos we inhabit might be the projection of quantum bits arranged on a boundary so vast it encompasses everything. This solves one of inflation's nagging problems: how the early universe could have been so perfectly uniform. If all points in space were literally connected at the fundamental level by being encoded on the same surface, their synchronization isn't a mystery, it's inevitable. Where this gets truly revolutionary is thermodynamics. The holographic principle implies there's a hard limit to how much information any region of space can contain, a concept called the Bekenstein bound. At the Big Bang, when the observable universe was smaller than an atom, this would have forced an extreme compression of data, like stuffing a library's worth of books into a single letter. Yet, unlike a classical singularity where physics breaks down, the holographic version preserves the universe's source code intact on its boundary, avoiding true infinities. It's as if the Big Bang wasn't the universe's birth, but its boot-up sequence, a rendering of deeper, simpler rules. Evidence might already be hiding in plain sight. If spacetime is fundamentally pixelated, a hallmark of holography, then extremely high-energy cosmic rays should reveal subtle granularity as they travel billions of light-years. Experiments like the Fermi Gamma Ray Space Telescope are hunting for these telltale glitches in starlight. Even more tantalizing are anomalies in the cosmic microwave background's polarization patterns, strange correlations that some physicists argue could be fingerprints of a universe encoded at its edges. Critics argue the theory swaps one mystery for another. What writes the hologram, and where does that surface exist? But supporters counter that it's no stranger than positing unseen dimensions or multiverses. Whether ultimate truth or stepping stone, the holographic Big Bang does something remarkable. It turns the universe's origin from a physics problem into an information puzzle, one where the answer might not lie in the stars, but in the unseen bits that make them shine. We think of neutrinos as ghostly afterthoughts, tiny, nearly massless particles that breeze through matter like it isn't there. But rewind to the universe's first second, and these cosmic phantoms might have been the puppeteers pulling the strings of reality. Neutrinos aren't just space's most abundant particles after photons. They could hold the missing clues to why galaxies, stars, and even we exist at all. Picture the cosmos just 1 second old, a seething plasma so dense that light couldn't travel an inch without colliding with another particle. In this chaos, neutrinos were the first to escape the maelstrom, decoupling from matter as the universe cooled. This neutrino decoupling wasn't just a minor event. It marked the moment these particles began streaming freely through space, their sheer numbers forming a cosmic background sea as fundamental as the microwave afterglow we detect today. But here's the twist. Unlike the smooth glow of photons, neutrinos might have carried faint density ripples, imperfections that gravity later amplified into the galactic superstructures we see now. Their secret weapon, mass. For decades, physicists assumed neutrinos were weightless. Then experiments revealed they oscillate between flavors, proof they must have some infinitesimal heft. That tiny mass changes everything. Even if each neutrino weighs a millionth of an electron's mass, their staggering abundance means they could collectively rival all visible stars in gravitational influence. Some models suggest these particles acted as cosmic scaffolding, their gravity subtly steering ordinary matter into the filaments and voids of the large-scale universe. But the real bombshell comes from relic neutrinos, those born in the Big Bang's first second, still drifting through space today. These ancient messengers could be hiding a time capsule of the universe's earliest moments. Unlike photons scrambled by later interactions, neutrinos decoupled so early that their energies reflect conditions before even the first nuclei formed. Detect them and we'd have a snapshot of reality at 1 second old, a window no telescope can peer through. The challenge: neutrinos are notoriously aloof. Trillions pass through your body every second, yet they interact so rarely that catching one is like snaring smoke with a net. Projects like the upcoming Ptolemy experiment aim to trap relic neutrinos using ultra-cold detectors the size of swimming pools, hunting for the faintest tick of a collision. Success would revolutionize cosmology, not just confirming neutrino mass but potentially revealing if these particles skewed the early universe's expansion rate or seeded dark matter's formation. Critics argue their impact is overstated, that without stronger interactions, neutrinos couldn't have significantly shaped structure. Yet simulations show even slight neutrino drag would leave detectable wrinkles in galaxy distributions. And if future telescopes find these fingerprints, it would mean rewriting the story of cosmic dawn, not as a tale dominated by dark matter and photons, but as a delicate dance where the universe's lightest particles tilted the balance toward everything we know. Whether architects or bystanders, neutrinos force us to confront a humbling truth. The universe's grandest structures might owe their existence to particles so elusive, we're only beginning to grasp their ghostly influence. What if the speed of light, that universal constant etched into physics textbooks, wasn't always constant? This radical idea turns Einstein's foundational assumption on its head, proposing that in the searing chaos of the early universe, light raced across space at speeds far beyond today's 300,000 kilometers per second. It's not just a tweak to the rules, it's a complete rewrite of cosmic history, one where the horizon and flatness problems solve themselves without invoking inflation's exponential expansion. The horizon problem has long haunted cosmologists. How could regions of the universe separated by billions of light years share nearly identical temperatures when light hasn't had time to travel between them since the Big Bang? Inflation's solution, a faster-than-light stretching of space itself, works mathematically but feels like a cosmic sleight of hand. Enter variable speed of light theories, where the answer is heartbreakingly simple. Light did have time to connect those regions because it moved faster in the past. Picture two cities separated by a growing river. If the river's current slows over time, boats that once crossed quickly now take ages. But their earlier, faster journeys could have established links now impossible to replicate. Flatness presents an even deeper puzzle. The universe's geometry is balanced on a knife edge between open and closed curvature so precisely that even a tiny deviation at the Big Bang would have led to runaway collapse or dissipation. Inflation forces this fine-tuning by stretching any initial curvature to near flatness. But if light speed was higher in the early universe, the cosmos could have reached thermal equilibrium naturally, smoothing out wrinkles before the speed limit dropped. Think of a souffle that puffs up perfectly because the oven's initial high heat stabilized its structure. No need to invoke a magical expanding force. The math behind this isn't just speculative. Physicists like João Megiddo and Andreas Albrecht have shown how dropping light speed invariance in the early universe can replicate inflation's successes while sidestepping its unanswered questions. In their models, light speed scales with temperature approaching infinity near the Big Bang's heat, then decaying to today's value as the cosmos cooled. This creates a phase transition akin to water freezing, where the laws of physics themselves shift gears. Observational clues might already exist. Some measurements of the cosmic microwave background show anomalous patterns in polarization, subtle swirls that don't quite match inflation's predictions but align with variable light speed scenarios. Even more provocative are hints that the fine structure constant, a dimensionless number governing electromagnetism, might have varied slightly over cosmic time, as reported in quasar light studies. If confirmed, this would shake physics to its core, implying that nature's constants are more like dials that the universe tweaked during its infancy. Critics argue that altering light speed undermines relativity's bedrock principles, risking a cascade of contradictions. Yet supporters counter that relativity itself emerges from deeper, possibly mutable laws, like how thermodynamics arises from atomic motion without contradicting it. The debate isn't just academic. Future gravitational wave detectors could settle it by probing the universe's earliest moments for imprints of primordial light speed shifts. Whether revolutionary truth or provocative thought experiment, variable speed of light theories remind us that even the most sacred constants might be artifacts of a deeper, wilder reality, one where the rules we take for granted were written in the fire of creation, not etched in stone. What if space-time wasn't always there? What if it crystallized from something stranger, like ice forming on a freezing lake? This is the mind-bending premise of quantum gravity, a theory that reimagines the birth of the cosmos not as an explosion, but as a phased transition where the very fabric of reality froze into existence. Picture the early universe not as a seething ball of energy, but as a chaotic quantum network, a roiling soup of interconnected nodes where concepts like here and there had no meaning. Then, in an instant, this frenzied web cooled and snapped into order, locking into the structured space-time we recognize today. At the heart of this idea is a radical shift in perspective. Instead of treating space and time as fundamental, quantum gravity suggests their emergent properties, collective behaviors of countless tiny quantum bits, or qubits, buzzing beneath the surface. Think of it like watching a movie. The smooth motion on screen emerges from individual static frames flashing by. Similarly, our continuous four-dimensional reality might be the macroscopic face of microscopic interactions we can't yet see. In the beginning, these qubits would have been wildly entangled, forming a dense, unstructured graph where no point was truly distinct from any other. There were no distances, no directions, just pure, unfiltered quantum potential. But here's where it gets transformative. As the universe cooled, this network underwent a cosmic freezing. The quantum connections that once allowed instantaneous jumps between any 2 points suddenly stiffened, locking into a rigid lattice where only nearby nodes could communicate. This phase transition would have created something astonishing: locality. Distances emerged not as pre-existing properties but as consequences, the number of hops needed to get from one node to another. Time itself might have crystallized from the sequence of these interactions, like a metronome ticking as the network updated. The implications are staggering. First, it solves the Big Bang Singularity problem elegantly. There's no need for infinite density when spacetime itself is still soft and mutable, just a gradual hardening from quantum foam to classical reality. Second, it offers a fresh take on cosmic inflation's uniformity. If the pre-spacetime network was thoroughly entangled, its freezing would naturally produce a homogeneous universe, no rapid expansion required. Even dark energy could find an explanation here as residual stress in the crystallized structure, like cracks forming in ice as it settles. Where quantum gravity truly shines is in its testable predictions. If spacetime is granular, high-energy cosmic rays should reveal subtle pixelation as they travel billions of light-years. Experiments like the Pierre-Auger Observatory are already hunting for these telltale glitches. Even more tantalizing are echoes of the transition itself. Some models suggest gravity waves from spacetime's freezing might still ripple through the cosmos at unique frequencies, one's next-generation detectors could soon uncover. Yet challenges remain. How exactly does a featureless quantum network give rise to the precise 4 dimensions we experience? Why 3 of space and 1 of time? Some versions of the theory invoke preferential growth in certain directions, like crystals forming along specific axes. Others speculate that higher dimensional graphs could project shadows resembling our reality, like a 3-dimensional object casting a 2-dimensional silhouette. Whether ultimate truth or stepping stone, quantum gravity forces us to confront a profound shift. The universe's beginning might not have been a moment of explosive creation, but a quiet settling, a cosmic dew forming on the web of quantum connections. And if that's true, then space-time itself isn't the stage for reality's drama. It's part of the performance, a role written deep in the script of existence. What if gravity isn't a fundamental force at all but a cosmic illusion, a side effect of the universe's relentless drive toward disorder? This radical idea, known as entropic gravity, turns Newton and Einstein on their heads, proposing that what we call gravity is actually the universe's way of maximizing entropy, the natural tendency of systems to become more chaotic over time. At the heart of this theory lies a staggering implication for cosmic origins. Gravity might not have existed in the early universe's first moments. Instead, it could have emerged as quantum information in the primordial void began to organize or disorganize itself. The theory's architect, physicist Eric Verland, didn't set out to rewrite cosmology. He was trying to solve a puzzle. Why does gravity behave so differently from the other fundamental forces? Electromagnetism and nuclear forces are quantum at their core, mediated by particles like photons and gluons. Gravity, meanwhile, resists quantization stubbornly, its hypothetical carrier, the graviton, forever undetected. Verland's breakthrough was realizing gravity might not need a particle at all. Imagine a crowded room where people start moving toward the exits not because of some invisible force, but simply because there are more ways to arrange themselves in the open space outside. Gravity, in this view, isn't pulling matter at statistics in action, a thermodynamic tendency toward higher entropy configurations. Apply this to the Big Bang and the implications explode. If gravity is entropic, then in the universe's earliest, hottest state where entropy was already maximized, gravity, as we know it, wouldn't have existed. Instead, what we perceive as gravitational attraction might have crystallized as the cosmos expanded and cooled, like frost forming on a window. This flips the script on structure formation. Galaxies wouldn't have clumped together because of some pre-existing force, but because quantum information in the void wanted to explore new, more disordered states. It's as if the universe's first law wasn't attract, but explore. Where this gets truly mind-bending is dark matter. Mainstream cosmology invokes invisible matter to explain why galaxies rotate faster than gravity predicts. But entropic gravity offers an alternative. What if dark matter isn't a particle, but a signature of how entropy gradients warp spacetime on cosmic scales? Verland's math suggests that the extra pull we attribute to dark matter could actually be the universe's way of rebalancing its information content, like a thermostat adjusting to maintain equilibrium. Observations of galactic rotation curves loosely align with these predictions, though the debate is far from settled. Critics argue entropic gravity struggles to explain phenomena like gravitational lensing or the precise acoustics of the cosmic microwave background. Yet supporters point to its elegant resolution of the Hubble tension, the discrepancy in cosmic expansion measurements by naturally incorporating scale-dependent effects. Future tests, like mapping the universe's large-scale structure with next-gen telescopes, could tip the scales. Whether final answer or stepping stone, entropic gravity forces us to confront a humbling possibility. The force that shapes galaxies and bends starlight might not be a force at all, but a cosmic byproduct, a shadow cast by the universe's endless dance toward chaos. And if that's true, then the story of gravity's birth isn't written in the language of particles or fields, but in the silent, statistical whispers of quantum information finding its way. What if the universe didn't need a creator because it was its own creator? This is the radical proposition of the self-creating universe, a theory where existence loops back on itself like a cosmic Ouroboros, swallowing its own tail in a feedback loop of creation. Picture reality as a set of dominoes arranged in a perfect circle. The first domino falls, triggering the next until the final domino somehow knocks over the first one again. No external hand is needed, the system sustains itself, an endless cycle where cause and effect blur into something stranger. At the heart of this idea lies quantum mechanics' most baffling quirk. Particles can pop into existence from nothing, borrowing energy from the vacuum as long as they vanish quickly enough. Now scale that up to the universe itself. Some models suggest that quantum fluctuations in a pre-existing void could have spawned a self-contained loop of space-time, a universe that, in essence, authorized its own birth. It's like a movie where the final scene reveals the protagonist was the director all along, folding the story into a twist so tight it erases its own beginnings. One version of this idea comes from loop quantum gravity, where space-time isn't smooth but woven from tiny, interlocking loops. In this framework, the Big Bang might not have been a singular explosion but a quantum bounce, a previous universe collapsing to a point where gravity reversed into repulsion, birthing our cosmos from the ashes of its predecessor. But here's the twist. The equations suggest this cycle could be self-sustaining, with each universe's death seeding the next one's birth in an infinite regression with no ultimate starting point. Even wilder are theories invoking self-referential physics, where the universe's own laws retroactively ensure its existence. Think of a computer program that rewrites its own source code as it runs. Some physicists speculate that quantum observers, conscious beings like us, might play a role in this loop, our act of measurement somehow stabilizing the universe's origin in a feedback spiral. It's as if the universe needed us to exist so it could exist, a chicken and egg paradox written in the fabric of reality. Critics argue this veers into metaphysics, but supporters point to concrete math. Quantum entanglement, for instance, allows particles to influence each other instantaneously across space, seemingly defying cause and effect. If microscopic physics can bend these rules, why not cosmology? And if future telescopes detect anomalies in the cosmic microwave background, patterns that resemble scars from a pre-Big Bang phase, it could hint at a universe forever rewriting its own origin story. The self-creating universe doesn't just challenge our search for beginnings, it obliterates the very idea. If reality can bootstrap itself into existence, then the question, why is there something rather than nothing, might have an answer as strange as the cosmos itself, because there had to be. From quantum fluctuations birthing reality from pure nothingness to black holes spawning entire new universes inside their depths, we've journeyed through a labyrinth of cosmic possibilities, each more astonishing than the last. These aren't just abstract thought experiments. They're legitimate scientific frontiers where the boundary between physics and philosophy blurs into something transcendent. Whether it's holographic beginnings rewriting the nature of space itself, or self-creating universes folding causality into a loop, every theory forces us to confront the same humbling truth. Our universe might not have played by the rules we once assumed were sacred. What's striking isn't just the diversity of ideas, it's how each one reshapes the very meaning of nothing. To some theories, nothing is a seething quantum foam pregnant with potential. To others, it's a two-dimensional surface encoding our 3D reality like a cosmic projector screen. And in the wildest models, nothing doesn't even exist because time itself might be an illusion, leaving no before for the Big Bang to emerge from. The audacity of these visions is matched only by their mathematical rigor, proving that when it comes to cosmic origins, even the unimaginable deserves a seat at the table. So, which theory resonates with you? The elegant symmetry of a cyclic universe forever bouncing between rebirth and collapse. The haunting elegance of the holographic principle, reducing all existence to information flickering on a distant boundary. Or perhaps the dizzying multiverse where every possible physics plays out in parallel realities. Drop your favorites in the comments, debate, dissect, and dare to imagine alongside fellow cosmic explorers, because this conversation is far from over. And let's be honest, we've only scratched the surface. For every mystery we've tackled, a dozen more lurk in the shadows. What ignited inflation is dark energy evolving. Are there deeper layers to space-time we can't yet perceive? The universe's greatest gift might be its refusal to surrender all its secrets at once. So stay curious, keep questioning, and remember, the next groundbreaking idea could be the one that rewrites everything. Until then, keep looking up and wondering what's really out